Yes, sir.
Okay. So now we come to look at what flash architecture is about. So again, we have row decoders and column decoders, and just like the DRAM, the address bus is shared here also. So what does that mean? When I say that the address bus is shared, what would that mean?
Square is structure.
Not okay. So either yes, it is either we can say it is a squared row, a square array, or we could say that it is something which is, or we could say it is something which is where you will have to send address in multiple phases.
Less resources.
Yes. Again, this is very critical over here because flash is always off chip. If the flash would be on chip, then again, you need not have this multiplexing of row and column address on the address bus. But if flash is, how do we put it, off chip, then there are a number of pins that are involved there, and that is what needs to be taken care of. So again, over here we have word line which goes on the control gate now, and the bit line which is connected to the drain. Is this clear? So notice there is this source switch. Source switch means ground connection being coming from here. And so what kind of a flash is this? This is the control gate on the word line connected to the control gate, and bit lines connected to the drain region. So what kind of flash is this? NOR or NAND? What kind of flash would be this? Hello? Yeah, why is this NOR?
Because
स्लाइड पे लिखा हुआ है.
अच्छा कहाँ लिखा है? नहीं सर, स्लाइड कहाँ लिखा है?
स्लाइड के टाइटल पे NOR लिखा हुआ है, but why is it NOR?
सर सोर्स कनेक्टेड है बिट लाइन से, तो वो देख के मैंने.
See, over here, every device is connected to bit line on one side and source on the other side. So all the devices are in parallel to each other. Any one of the device allows current to flow, bit line would discharge. Because that is the logic that is being applied, this is NOR.
Yes, sir.
Okay. So when we have this NOR flash, what is being done? To do the read operation, what do? We just take the bit line, the word line to a level which is between the VT of say 0 and 1. Okay. Now at this particular word line level, all these devices, they will sync current, and the devices over here will not sync current. The cells that sync current, they are said to have, let us say, 0 stored on them. The other ones are said to have 1 stored on them. Is it okay?
So ये वही सेंस थ्रेशोल्ड वाला पार्ट है ना?
Sorry?
जिसमें डिफरेंट थ्रेशोल्ड चाहिए थे हमको, हाई वीटी और लो वीटी, जो उनका एक बीच में मार्जिन होना चाहिए.
Yes. So हमने यहाँ पे we've ensured that the spread of let us say cell storing 0 is 3 volts, The cell storing 1 is 7 volts. So there is a huge margin in between them, and we are keeping void line at somewhere in between them. Okay.
Yes.
How do you do a write? How do you do a program? So that was the read operation. How do you do a program or an erase? So what happens is, let us say there are so many of these word lines there. You would, to erase this thing, you would put word line at -10 volts. And you would put bulk at 6 to 8 volts. What will happen?
FN tunneling will happen. So
FN
because of
tunneling will happen. Yes, FN tunneling will happen, and all the electrons that were there in the floating gate will be repelled into the bulk region. Bulk has a high positive voltage. Control gate has a very high negative voltage. So all the electrons in the control gate will get repelled, and you will have cell VT again, which is in this range. Okay, when I want to program, we already discussed this last time also. When I want to program, word line is at +10 volts. Bit line is at, let us say, 5 volts. The other bit line is at 0. So what is happening?
Charge will be trapped.
Yes, you create a high VDS across the gate, across the device. So charges are energized, and then you have a vertical field also. So charges, electrons are attracted to the gate. They will breach through the gate oxide and enter into the floating gate there. As a consequence, VT would increase. Is this clear? Any questions?
Sir, what does F mean in this?
Floating.
Okay. So why are we keeping select line SL as floating?
So it is not select line, it's source line.
Okay, sorry.
Yeah, the source line is also left floating because you are doing FN tunneling into the bulk.
Yes. Okay, okay. So we want them to escape via bulk and not through source. Okay. Obviously they won't be able to. Okay, got it.
Yeah. And then that is the read operation that we just discussed.
सर जस्ट फॉर क्लैरिफिकेशन जो 163 वोल्ट था वो जो ट्रैप्ड हो रहा है उसका वोल्टेज की वजह से 1 to 3 वोल्ट और
1 to 3 volts VT इसलिए रह गया बिकॉज आपने जितना भी चार्ज इसमें था आपने उस सारे चार्ज को भगा दिया.
ओके
आपने उस सारे के सारे चार्ज को रिपेल कर दिया फ्रॉम द फ्लोटिंग गेट एंड इट हैज गॉन इनटू व्हाट डू वी से
इन सोर्स साइड.
यस, ठीक है.
यस
So the layout of such a cell appears something like this. The green one is the source line that is sent through the diffusion layer, and yellow one shown over here is the, let us say, control gate. Floating gate is shown with this light gray kind of a thing, and then there is isolation between the cells. Now, this is STI. And do you see that with every cell, there is a set of contacts that are there and everything that is there? So what happens? It takes a little bit more area than you would have desired. This is how the cell would look like. Sorry, this is how the cell would look like. You see the control gate. This is the control gate over there. and these are the floating gates. The control gate is one continuous line. Why is that? Why is that the case? Because it is the common word line. This is the row. This is word line view, which is cross section at this place along the B axis. So control gate is continuous. Floating gate is just above the device, and this is the source and drain region there. Now, if I intersect or intercept from here, then this is the view that I see. I see the contact for the bit line, and I see the source drain region for the device also there.
So the thin white strip between CG and FG, is that the dielectric, very thin?
I'm sorry?
So the dielectric is very thin, like,
This one.
and in between CG and FG also.
Yes, this one also.
Okay, got it.
Okay. Any further questions? Is this clear? Okay. So now in a NOR flash, then what you do? You organize the entire memory into blocks. And in every block, you have these NOR cells which are arranged with the help of row decoders and everything. And this is the, every cross section over here represents such a bit cell, such a flash cell over there. When you want to read, now let us say you were storing 2 bits in this memory cell. Let us say, if you are storing 2 bits in this memory cell and you want to read, then there are 2 ways that you could read. One way is that you apply 1 voltage on the gate and then measure the current that different bit lines are discharging. So what does that mean? That means that the current that is consumed by a cell, which is, let us say this is 0, 0, 0, 1, 1, 0, and 1, 1. So current consumed by 0, 0 is obviously 0. 0, 1 is equal to IC2. 1, 0 is equal to IC3, and 1, 1 is equal to IC4. If you can identify what is the current that is being sunk into the memory cell, you can tell what data you are storing, what 2 bits you are storing in your memory cell. Is this part clear? So you will need a current sense amplifier, current mode sense amplifier. Is the left figure clear?
Yes, sir.
Now, when you want to read, what do? When you want to read in the voltage mode, what do? You say that I want to measure when is IC getting sunk in my particular cell. So let us say for one cell, IC got reached at VG4 itself, and another cell, IG got reached at VG1. So what this means is that this is, let us say, 0, 0. This then is 1, 1. And you could say 0, 1, 1, 0 over here. Clearly, when you operate in voltage mode, you have fixed the IC per cell. So you require lesser currents. It is lesser power, and also, in one go, you could be able to make out a lot of stuff. So parallelism is also high. Are you able to see this? Any questions?
So just for clarification, with one current measuring, we can read around four states, right? we can read that 4 states only with one current measures.
Only with one current value we can reach we can identify what voltage will my cell sink that kind of current, and I can kind of estimate the VT of my device.
Yes, sir. From there we can decide 00 or 01.
Yeah.
So okay. I'm just confusing in if there will be 4 devices connected and to 1 bit line, and okay, that case would not create because the word line would be selected only.
I'm sorry.
Yeah, got it, sir. थोड़ा confuse हो गया.
ठीक है. So if we say that we were doing, say, let us say voltage mode read operation, then what does the circuit looks like? What does the circuit look like? It could appear something like this. I want to sync, let us say, some cell current, IBL. Okay. So this is my bit line, and I know what is the cell current that is being sunk here. Okay. With this cell current, I kind of put a bit line limiter that more than this current will not be sunk by the bit line. And there is this CBL which I discharge with the current of IC. And when I start to do that, I kind of mirror it to get the current KIC go in this arm. A voltage would appear over here. Okay. A voltage would appear over here. And depending on IR minus KIC, there could be some charge that would flow from a high voltage sense amplifier into this region. This output is amplified. So this ID is then amplified through this amplifier stage. You see, यहाँ पे 1 है, it is H over here. So this is amplified with over H times over here. And when the steady state is reached, we simply measure the VG. VG at this point tells me what is the voltage at which that kind of current is being discharged from my bit line. So I will be able to estimate whether it is V4, VT3, VT2, or VT1. Questions?
So by measuring at the end, we are measuring the VG, and by measuring VG, we are saying what is the, yeah, okay, sir.
Is that okay?
Sir,
Yes.
ID, who is controlling ID? Can you tell again?
So IR, I have a reference current. K times IC plus ID should be equal to IR.
Okay, so as KIC varies, so does the ID, and then IC amplifies to give us the output basically. Okay,
Yes.
got it.
Is it clear? So we're just amplifying K times once and then doing this subtraction at this reference voltage and then multiplying it with H times.
So how we are deciding this K and this H value? Like on what basis?
I'm sorry?
How we are deciding this K value and H value? On what basis we are deciding these values?
That is the kind of current budget, the speed that you need, and so on. What is the
So
power budget that you want to keep, and what is the speed at which you want to operate?
Okay. Sir.
Because if the K is large, a large amount of current would flow, the references. So it depends on the current that you want to sync and the sensitivity of that you require of your circuit. All these factors.
Okay, sir.
Okay.
One basic doubt. Why did you say that current mode of read operation is not parallel while okay, I got it why voltage would be parallel, but why that current mode would not be parallel?
Why current
Because
mode?
since we are only applying one gate voltage and it is giving us four different currents, so why can't we sense them simultaneously?
So okay. So if I want to sense them simultaneously, I will need to have 4 sense amplifiers,
Yes, sir.
and then I can sense them simultaneously. Yes.
So, sir, what is the contrast between parallelism in both the
Contrast
gates?
is this kind of current is flowing. Over here, you have limited the current to IC.
Yeah, the power dissipation is
Power
one factor.
dissipation is a clear contrast.
Okay, so that is the only thing.
Yeah.
Okay, thank you.
Okay.